Okay, gentlemen. Today we're talking about moles. We're going to continue talking about them and doing molar conversions. Just a reminder, a mole is a unit, and it's just a counting unit. It just means that you have 6.02 times 10 to the 23rd, this many, right here, that many of something. In particular, what is measuring in chemistry is representative particles. And a representative particle is just the base unit of a substance. So for elements, the base unit is atoms. For molecular compounds, for example, water, the base unit would be the molecule. An example of an element would be, I don't know, like iron. So if you're measuring a mole of iron, you're measuring iron atoms. If you're measuring a mole of water, you're measuring H2O molecules. And for ionic compounds like, I don't know, calcium chloride, CaCl2, you're measuring formula units, which is just literally whatever is in the formula. So if you have a mole of calcium chloride, you have a mole of these CaCl2s. That's all the mole is. It allows you to count really, really huge amounts of stuff and put them into numbers that we can use. And this is important because, again, any amount of actual matter that we would be manipulating or using contains a ridiculously huge amount of molecules and atoms. So we are able to translate from that atomic and molecular level to something we can measure and use fairly easily. Because when we write chemical equations, we write them out for individual atoms and molecules. And that's actually what's going on. But we can't work at that level. We have to work in things like grams or liters or things that are easier for us to measure. So today, what I'm going to do is I'm going to go over a couple of the problems from the moles worksheet number 1, run through a couple examples, and then I'm going to go through a couple examples of what is going to be your in-class assignment today, which is the Molar Mass worksheet number 2. So first, just going back to the moles worksheet number 1, this is the one that was already assigned to you for homework. Just a couple examples. Determine the number of representative particles in each of the following, and show the factor label method. So you got to show your work for these. And I'm just going to do these 2 examples, and then we will move on. So let's say we have 0.250 moles of silver. Well, if we want to find out how many representative particles in that, we have to convert from moles to particles. Our conversion factor from moles to particles is going to be 6.02 times 10 to the 23rd particles per 1 mole. That can also be reversed, and you could say 1 mole has 6.02 times 10 to the 23rd particles, depending on which way you're converting, whether you're going from particles to moles or moles to particles. So let's look at this silver issue. We got 0.250 moles of silver. Let's convert it into particles. So first step in any conversion, 0.250 moles of silver. Silver is Ag. Put that over 1. And then we put in our conversion factor. And in this case, our conversion factor is going to be, we want to go 2 particles. So particles is going to be on the top. So 6.02 times 10 to the 23rd over 1 mole of silver. Now the type of particle depends on what type of substance you're dealing with. In this case, we're dealing with an element, silver. So it's going to be atoms. So this is just a simple multiplication problem. 0.250 times 6.02 times 10 to the 23rd. Remember to use the E button on your calculator. It would be 6.02E23. That will make your life easier. And what you end up with is, excuse me, this. You end up getting 1.2 5,1, and you do go to 3 sig figs because you start with 3 sig figs, times 10 to the 23rd moles of silver. And you should label your answer as moles of silver. So both the unit, moles, and... Oh, I'm sorry, that's not moles at all. It should be atoms. That's my fault. I'm trying to do too many things at once here. Atoms of silver. But you should label it with both the unit, atoms, and the substance silver. Because there will be a point where we will be working with more than one substance at once, so you want to specify which substance. Chemical formulas and symbols are always fine. You don't have to write out silver. You can. That's okay too. It's entirely up to you. So one more example of this. We'll start with 35.4 moles of carbon dioxide and convert that to particles. So take what you're given, 35.4 moles of CO2. Put that over 1 and set up your conversion. We're going to want moles of CO2 on the bottom because that's what we want to get rid of. So in this case, it's going to be 1 mole of CO2. And 1 mole of CO2 is 6.02 times 10 to the 23rd. And now again, we have to look at what type of particle. This is a molecular compound. CO2 made of 2 nonmetals, molecular compound. So we're going to be talking about molecules. And yeah, it's a bit of a pain to write, but you should still write it. And again, this is just a multiplication problem. And if you do the multiplication, what you get is 2.13 times 10 to the 25th. And again, you should put the unit and the substance. Molecules is what we were measuring or converting to. CO2. So those are 2 basic examples of converting between moles and particles. You can also go back the other way. If you're given particles, you divide by 6.02 times 10 to the 23rd to go to moles. Again, you kind of want to get used to using that E button on your calculator. So 6.02 E23, that will make your life easier, and it'll make annoying mistakes less likely. Because sometimes the calculator, if you don't use the E button, it does a different order of operations than you would like it to. Okay, so we just talked about how to switch from particles to moles and moles to particles. Use that 6.02 times 10 to the 23rd. That's the number of a mole. That's Avogadro's number, so it has several names. And now we're going to talk about how to go from moles to grams, which is often the more helpful and most commonly used conversion, because usually in the lab we measure things in grams. To go from moles to grams, we have to figure out what's called the molar mass, or molecular weight, of different elements or compounds. For elements, it's really easy. The reason they picked that weird 6.02 times 10 to the 23rd number was because that allows them to take the atomic mass, the mass of an atom in AMUs, and just stick grams after it and call it the molar mass. It turns out that means it would have 6.02 times 10 to the 23rd particles, so they just took that number and called that a mole. So on the periodic table, you can look up the molar mass of any element. It's the atomic mass, the average atomic mass, but just in grams. So for hydrogen, it would be 1.01. For helium, 4.00. I'm going to go to the hundredths place when I round. Lithium, 6.94. So that means in a mole of lithium, 6.02 times 10 to the 23rd particles of lithium, you have 6.94 grams. Or if you have 6.94 grams, you have 1 mole. So if we want to figure out an individual element's atomic or molar mass, we simply look up the atomic mass on a periodic table, the average atomic weight, and put grams after it. And that's it. That's all you have to do. But that gives us only how to figure out elements. A lot of the stuff we work with are, in fact, compounds, like these guys. Either ionic or covalent compounds. It works the same either way. To figure out the molar masses of these, all you do is you add up the parts. So that's all you have to do for this. So sodium hydroxide, for example, and by the way, this is off your worksheet for today, the Molar Mass worksheet number 2. So I'm going to end up going through about half the problems on that. So you might want to follow along on that worksheet. So sodium hydroxide, this first one, NaOH. Well, sodium hydroxide is made out of sodium, an oxygen, and a hydrogen. So we just got to figure out how much each of those weigh and add them together. There's only one of each of them. So to figure out how much each of them weigh, you go to the periodic table. Sodium, 22.99. Apparently I can't round on the fly. So 22.99. Technically, the unit here would be grams per mole. I'm not going to add the unit till the end just because of space considerations. Oxygen. Look at oxygen. Oxygen that rounds to 16.00, rounding to the nearest hundredth. So oxygen is 16.00. Hydrogen we already looked at briefly, but hydrogen is 1.01, again rounding the hundredth place in this case. So 1.01. If you total those up, you end up with 40.00. I'm getting ahead of myself. 40.00. And the unit for molar mass is grams per mole, because that's how many grams are in 1 mole of that thing. So sodium hydroxide, NaOH, weighs 40 grams per mole. If you have 40 grams of sodium hydroxide, you have 1 mole. Let's go on to the next thing. That's phosphoric acid, but we didn't learn naming acid, so I wouldn't necessarily expect you to know the name of that, but it's phosphoric acid. It's made out of 3 hydrogens, a phosphorus, and 4 oxygens. So again, we're just going to add these up. Now, I'm going to do some multiplication, but you could just add hydrogen plus hydrogen plus hydrogen plus phosphorus plus oxygen plus oxygen plus oxygen plus oxygen. But you know, when you're adding multiple times, that's just multiplication. So this is how I set it up. If you just want to do all the addition, you can do it that way too. So I'll set it up like this. It's made out of hydrogen, phosphorus, and oxygen. Hydrogen equals 1.01. Phosphorus, and we saw that already. Phosphorus, well, I'm going to look that one up because we didn't use that one yet. Phosphorus over here equals 30.97. And oxygen, we saw already, is 16.00. But there's not just one of each of these. So hydrogen, there are 3 of. Phosphorus, there's only 1 of. And oxygen, there are 4 of. So I'm multiplying by those numbers. Yes, I realize that multiplying by 1 is unnecessary, but it keeps everything lined up nicely. So this is how I prefer to do it. Hydrogen times 3 is 3.03. Phosphorus times 1 is 30.97. I'm pretty confident on that one. And oxygen times 4, so 16 times 4, is going to be 64.00. Okay, so if you total all that up, you end up with 98.00 grams per mole. So 1 mole of phosphoric acid weighs 98 grams. Magnesium chloride, well, it's made out of magnesium and chlorine. So let's add them up. So we got a magnesium. And that's going to equal, well, we have to look that up. We haven't seen that one yet. Magnesium is 24.31, again rounding to the hundredths. Chlorine is, we'll look it up, 35.45. But of course there are 2 chlorines. So technically this one is times 1, and this one is times 2, and that equals 24.31, and this equals 70.90. So, again, because we don't just have one of each of these, we actually have to do the multiplication. You don't have to show the times 1. You don't even have to show the multiplication. I trust that you can do this on a calculator. But you may want to check your work and just make sure you aren't messing it up. It's fairly easy to look up molar masses of stuff. So you add those together, and the total you get is going to be 95.21 grams per mole. So finally, we have a bit of a tricky one. Move all this over. There we go. So, this is ammonium sulfate. Ammonium is the only positive polyatomic ion. Sulfate's a negative polyatomic ion. So this is an ionic compound, and it's, as far as we're concerned, it has 4 different elements. It's kind of a bigger compound. But we can still do it. It's just adding. You just got to be careful. One of the tricks with this one is it has parentheses. So this is made out of nitrogen, hydrogen, sulfur, and oxygen. Nitrogen, we haven't looked up yet. So nitrogen is 14.01 grams per mole. So we'll go back and plug that in. Hydrogen, we've seen a bunch of times, 1.01. Sulfur, we haven't seen yet, so we'll look it up. It's 32.06. And oxygen, we've seen, and it is 16.00. Now, this is where this is a little tricky. Clearly, there's more than one of most of these elements, but you got to be careful with that parentheses in there and how many there are. So, when you have a parentheses like this and a subscript outside, that distributes in. In other words, we have 2 of everything inside. So you have 2 NH4s, which means you have 2 nitrogens, because there's 1 nitrogen inside, and multiply that by 2, but also 8 hydrogens, not oxygen, excuse me. So we have 4 hydrogens inside, and there's 2 of them total. 4 times 2 is 8. So it distributes in. That 2 distributes in. There's only 1 sulfur, so times 1. And there are 4 oxygens, so that's times 4. And then we simply do the math on that. And we get 28.02 for the nitrogen. 8.08 for the hydrogen. 32.06 for the sulfur, and finally 64.00 for the oxygen. And then these all total to 132.16. And again, we get grams per mole. So, yeah, it's big. It's kind of a pain to do, but it's just adding. So, if you're careful, you just add all that stuff up. You look up the weights, add it all up. Look up the molar mass, add everything together. That's how you get the molar mass. Now, why is this important? Because this lets us convert from moles into grams, or grams back into moles. So it lets us go from moles, which we're going to deal with when we deal with chemical equations, to actual grams, which we deal with when we actually put the ingredients in. It allows us to go to kind of translate up to the amount we actually use. So molar mass is the conversion factor between grams and moles, so we have to figure out the molar mass of every chemical we use if we want to convert it from between grams and moles. Okay, so now I'm going to do 3 of the conversion problems from this worksheet. So about half of them. So in this one, it asks how many grams are there in 0.02 moles of beryllium iodide, and it gives you the formula, BeI2. So whenever you're going from grams to moles, you're going to need, or moles to grams, either way, you're going to need the molar mass, which I already figured out. The molar mass of BeI2 is this. You can see my work there, but we just did a bunch of those, so I'm not going to go through that. So this is a conversion. You're converting from moles to grams. Take what you're given, 0.02 moles, BeI2, put it over 1. I'm going to move this down. Not made a good use of space here. And then you plug in your conversion factor. And in this case, we know that 1 mole of beryllium iodide, well, we know exactly how many grams that weighs. That's what the molar mass is. It weighs 262.81. So that molar mass, that is the conversion between grams and moles. In this case, we want the moles on the bottom so they cancel out and the grams on top. And then, if you do the math, this is just, again, a multiplication problem. You end up with 5.26, which, because I only have 1 sig fig, I'm going to convert to 5 grams of beryllium iodide. The reason there's only 1 sig fig is because 0.02 only has 1 sig fig. I'm not going to kill you guys on rounding, but I'm going to continue to model doing it the correct way. So that's all that is. You have to figure out molar mass in order to convert from grams to moles, or back from moles to grams. So let's look at another one. How many grams are there in 3.3 moles of potassium sulfide, K2S? So again, we're just going to have to figure out the molar mass of potassium sulfide before we do anything else. So I'm going to do that and come back. So I figured out the molar mass of potassium sulfide. It's 110.26 grams per mole, as you can see here. And that's what's going to be my conversion factor. So again, we'll take what we're given, put it over 1, 3.3 moles of K2S. Put that over 1, and then we plug in our conversions. We know that in 1 mole of potassium sulfide, K2S, there are 110.26 grams. And that's it. Moles cancels out. You end up with grams. And if you do the multiplication there, the result is that you end up with, well, first, the raw number is 363.9. We only have 2 sig figs, so 360 grams of potassium sulfide. So, again, these are a little harder because you have to figure out the molar mass, but these are just basic conversions. To convert between moles and grams, you use molar mass. And to find molar mass, you just look up all the atoms involved on the periodic table and add it all up. So we're going to do one more, and this one's going to be going back the other way. We're going to be giving grams and go back to moles. And again, since the grams to moles conversion or moles to grams conversion, you need to figure out molar mass. So I'll do that. So I've determined the molar mass of silicon dioxide just by adding up 1 silicon and 2 oxygens, and that molar mass is 60.09 grams per mole. So now I can set up my conversion. Again, start with what you're given. In this case, 3.4 times 10 to the negative 7th grams of silicon dioxide. Put that over 1, and we just want to set up a conversion factor now. In this case, we want the grams of SiO2 on the bottom, and we want to go to moles. So we know that 1 mole of silicon dioxide is 60.09 grams. So we plug those numbers in. Oops. And again, now this is a division problem, and you want to be careful for the 3.4. You want to do 3.4 E negative 7. Use the E button. That'll make your life easier. But if you do the division, you end up with a raw number of something like 5.66 times 10 to the negative 9th. But I'm going to round to sig figs, excuse me. And we only have 2 sig figs in the initial question, 3.4, so we'll go to 5.56 5.7 times 10 to the negative 9. So the final answer will be 5.7 times 10 to the negative 9th. And again, moles of silicon dioxide. So both the unit and the substance in the answer. And that's it. Those are the examples I'm going to go through. And hopefully that was helpful. You should be able to complete the rest of the worksheet with the very similar questions. Again, just be careful when you do the math. This isn't too hard. Make sure your units are set up, your conversion is set up so your units cancel out. But when you're going from grams to moles or moles to grams, you use molar mass. And when you're going from moles to particles or particles to moles, you use 6.02 times 10 to the 23rd.